Hey, what's up, everybody? Mr. Murray here, Mr. Murray's Mathland. And today we are taking a look at evaluating definite integrals from a graph. So, purely from a graphic standpoint. And really, this is designed to be before you've even learned how to do one algebraically with the fundamental theorem of calculus. So, okay, let's jump right into this. We have the graph of f of x here, and we are evaluating the definite integral of f from -2 to 5. And as you start to become fluent in calculus, you want to kind of read it in that order from the bottom limit to the top limit, in that order, -2 to 5. And you want to make sure that goes chronologically in order, -2 to 5, from smallest to biggest. Okay, so here is the big takeaway. The word that's associated with a definite integral more than anything is area. That's really the big deal. Slope is associated with derivatives, area is associated with integrals. So what it's going to give you is the area under the graph between -2 and 5, between the graph and the x-axis. So here's -2, here is 5. The value of this definite integral is going to be that area right there, between there and the x-axis. Notice I'm not going beyond that. And another thing that's worth mentioning right now, we're going to see it in a few problems here, is that it's going to give you the area, but it's going to give you the signed area. And above the x-axis, area is positive. Below the x-axis, area is negative. Not area in a geometry sense, which is always a positive thing. But if you have been doing Riemann sums prior to this point, you know you're using the y values of the function to get those areas of those rectangles or trapezoids or whatever. So if you're above, the y value is going to be positive, and if you're below, the y values are going to be negative. So that'll be, sort of negative area, which will represent kind of a loss of whatever when you start to apply these to word problems. So, for example, here's maybe a nice, easy way to understand why you're doing what you're doing. Look at this equation here. It's a horizontal constant, y equals 3. Imagine that was like a velocity or a speed. You were going 3 meters per second, and you traveled it for a time of -2 to 5. That's a total time interval of 7. And if you traveled for 3 meters per second, for 7 seconds, for an interval of 7 seconds, that would give you a total or accumulated distance traveled of 21 meters. And that's really what you're dealing with here. This total area is 21. It's a big fat rectangle above the x-axis, so positive area. So that is the value of this definite integral, 21. So let's take a look at a couple other problems here, just so we see variety. Evaluating this f of x, notice now it's a line with a negative slope. This definite integral from -2 to 3, again, make sure that goes in order. And let's take a look. Here's where -2 is, and here's where 3 is. And so now notice that the graph dips below the x-axis. So you've got two portions here. Let's think of the area that's kind of trapped in between the function and the x-axis. There's that triangle, and then it dips below the x-axis, and you have another triangle. And so when you're above the x-axis, that represents a positive area or a net gain. And when you're below, that represents a loss or a negative area. So let's take a look. This is a triangle with a base of 3 and a height of 3. Area of a triangle is 1/2 base times height, so 1/2 3 squared, which is going to give you 9 halves, or 4.5. And this area of this triangle right here would be 1/2 of this base of 2 and this height of 2, or -2 if you wanted to think of the y value. which is why that area is going to be considered a negative value. So the area of the triangle is 2 in a geometry sense. But in a calculus sense, we're going to assign a negative value to that because it represents a loss of position. Maybe now the velocity, you're moving backwards, so you're losing some of that position you gained between -2 and 1. To get that total value, you add up those areas. So +9/2, and then when we went backwards, that was an area of -2, so we take away 2. And of course, that's, 4.5 minus 2 is 2.5, or if you want to answer with a fraction, that's 5/2. So that cumulative value is 5/2 or 2.5. And there we go. That's what a definite integral is, that accumulated area or signed area. And let's take a look just at a few more so you get comfortable here. Good to see a variety here, but that's really what it is. If you get that concept down, you can handle any of these, assuming you can find the area with some nice geometry. Okay, so this one right here is asking for the definite integral from -3 to 5. Again, that's going in order. So -3 is right here, and 5 is right here. That's where we're going to end up. And this, between -3 and -1, we are below the x-axis, so there's going to be some negative area there, but then the graph goes above the x-axis, so you're going to have some positive area. You're going to gain whatever it is you're representing, and then between 3 and 5, it's still above the x-axis, but it's a triangle. Okay, so let's just find these areas and add them up. So this right here is another 2 by 2 triangle, so that would be 1/2 2 times 2, which would be 2, but we assign a negative value to it because it's below the x-axis. Now this right here, just be careful with your geometry if you're a little rusty. This is a semicircle here with a radius of 2. Hopefully you can kind of see that. The center is right there. The radius in all directions is 2. 2 units up, 2 units right, 2 units left. So the area of a circle is pi r squared. So the area of a semicircle would be, of course, half of that. So 1/2 of the radius squared is 2 squared is 4. So 1/2 of 4 pi would mean this area is 2 pi. And then where you've got a triangle here on the end, which again is above the x-axis, so we're going to assign a positive value to its area, and that's a base of 2, a height of 4, so the area is 1/2 base times height. 1/2 2 times 4 is going to be 4. So here's what we got. Let's add up that grand total. We started with an area of -2. Then we gained that semicircle's area, which is 2 pi. Then we gained that triangle's area, which is 4. And let's just combine our like terms and say that's going to be 2 plus 2 pi, or 2 pi plus 2. And there we go. Okay, last example here, just because I've been saying it in each of these problems, and here's one where it's not the case. Notice, if you're already looking at it, maybe you've spotted this. This one starts with 6 and goes to a -5, and that's starting here and going backwards. And when it's out of order, that means everything's the opposite. If you were thinking about a position, that means you're kind of taking away everything you've gained, going in reverse, backwards in time. So if you haven't learned this trick prior to this point, this is one thing you can always do, is that you can switch the order, put the -5 on the end, on the back on the bottom where it belongs, and 6 on the top, but then take the opposite value of it. And so that's how you handle something that's out of order. And so now we can treat it like we just were, and everything that's above we can assign a positive value to its area. Everything below the x-axis, a negative value. Otherwise, if you want to try to do it then you've got to try to switch everything. Everything that's above is negative, and everything that's below is positive, and just that can get a little confusing. So I'm a big fan of switching the order and just putting a negative out in front, looking at it the way you're used to. Okay, so here's what I'm looking at here. Just be careful how you interpret this. We're going all the way from -5 to 6. And notice we got a lot of positive area. We've got this right here. That's a big fat rectangle. Actually looks like a square, a 3 by 3 square. And then you've got this semicircle, but this time the semicircle is kind of sitting tangent to the x-axis. It's kind of, sitting on it like a bowl. So this region trapped between the semicircle and the x-axis is what you've got to find, those little crusts there. And then you've got another triangle, and then finally you've got this one little triangle here on the end that's below the x-axis, the little sliver. Okay, so starts pretty normally here. I would think the area of this square, as we said, is 3 by 3, so its area is going to be 9. It's above the x-axis, assign a positive value. Watch out for how we handle this right here. Those little crescents there, those little corners. You want to, if you're a little rusty with your geometry, maybe this is not a big deal for you at all, but sometimes my students have a tricky time. Picture a big rectangle, right? It's just a big rectangle. Close that off, and then we're going to subtract out that semicircle area. That's really what's going on, right? That rectangle, and we're going to take out that semicircle, and that should leave you with those little corner pieces there. Okay. So the rectangle, again here, what we're doing, rectangle, we're going to subtract that semicircle. So the rectangle, pretty easy stuff, I think. That is a 3 by, goes from -2 to 4. That's a 3 by 6 rectangle. So its area is 18. We're going to subtract out that semicircle, which is again half pi r squared. And the radius of this semicircle, let's be careful, locate that center there. If that diameter was 6, the radius is 3, in whatever direction you want to look at. So that's going to be half of 3 squared is 9, half of 9 pi, or 9 pi over 2. And then you've got a little interesting thing that happens here. You've got this little sliver of a triangle here between 4 and 5. And if you want to find its area, it's a height of 3 and it's a base of 1. So that is 1/2 of 3 times 1. That's 3 halves. But sometimes you'll find that this kind of happens, and it's kind of nice. Look at when you dip below the x-axis, that's also a 1 by 3. So it has the same area, except it's going to be negative. So these two right here will kind of cancel each other out. It's like going forward 2 steps and then going backwards 2 steps. They just undo each other. So you can kind of ignore them. And in the future, if you were in a rush, you wouldn't even have to bother finding their area. Just ignore them and notice they cancel out. All right, so now let's put this all together. Just remember we are doing the opposite of our grand total here, our net area. So I'm just going to put a negative out in front, use a big set of parentheses, and now let's look at our areas here. So we have 9 that came from this square. This region in the middle we're adding on that 18 minus that 9 pi over 2. And then on the end, it would be that plus 3/2 minus 3/2. So they cancel each other out. I'm not even going to bother with them. And so, yeah, just be careful here. This is 27 minus 9 pi over 2. But then we're taking the opposite of the whole thing because that was out of order. So that's -27 plus 9 pi over 2, or 9 pi over 2 minus 27. However you want to, kind of say it. But okay, hopefully you saw a good variety of, geometry and little quirks in here, and you have an idea of how to evaluate these. The big question then is, what if it's not such a nice geometry figure to find the area under? What if you got a parabola or a crazy polynomial? And that's where the fundamental theorem of calculus comes in. So check that out in a future video. And we'll see you later. If you have any questions, just reach out and ask. Keep working hard, kids.